introduce Michael Hecht. Mike is the Associate Director for Research Management at the MIT Haystack Observatory since 2013. He has been the principal investigator for the MOXIE Oxygen ISRU demonstration experiment on NASA's Mars 2020 Perseverance rover. In his previous position at NASA's Jet Propulsion Laboratory, Mike served as the PI and instrument manager for the MECA soil analysis suite on the Phoenix Mars mission. And then in addition to his Mars exploration activities from afar, Mike has served as Deputy Project Director for the Event Horizon Telescope Project from September 2019 to August 2020, and shared in the 2020 Breakthrough Prize for Fundamental Physics. That's enough of me, and let me turn it over to Mike.
Thanks much, Harry. I'm pleased to be here today, and I have sort of a generic set of slides that I customized it a little bit, but I don't know your backgrounds very well, other than generally in the computer biz. I go way back there as well, but my path diverged more into physics and planetary science since the days of playing around with VAXes and whatnot. But again, feel free to deflect me and to stop and ask questions and move in other directions if it so pleases you to do so. Okay, I'm going to share sound. I'm going to share PowerPoint. And I will say in advance that there's a ton of stuff out there on the Perseverance mission that is much better than anything I can present. It's on the web. NASA prepares wonderful videos and all sorts of things. So I'm going to refer you to those if you want to see, more whiz-bang graphics. I'm going to focus on MOXIE. This is the first time we've put a chemical factory on another planet. ISRU is an acronym for In Situ Resource Utilization, which most people casually refer to as, describe as living off the land. And as I like to say, LOL was already taken as an acronym, so we had to call it something more NASA-like, ISRU. But that's the idea. The idea is to take something you find on another planet or the moon more typically and make something out of it so you don't have to bring it with you from home. That's the idea. So anyway, I'm going to talk about what it's really like to really do it and not just talk about it as people have been doing since the days of Wernher von Braun. So let's start with a couple of basics about going to Mars. If we were not living in an electrified society and we would go out at night and there would actually be dark skies, and we would do this every day and we'd look at the dark skies, we would be intimately familiar, as our ancestors were, with the planets and the stars. And as the planets move through the skies, Jupiter is super bright these days, Saturn is up, and Mars is just unmistakable as a bright orangey red, it's rusty, that's why it's that color, orangey reddish dot in the sky. And as the seasons go by, it goes higher and higher in the sky and gets brighter and brighter during the night, and then eventually wanes. And that's a 26-month cycle. So you all would have known that if you had been born 200 years ago. Okay. And that's important. Okay, that's important not just for astrology. And I've sort of always joked that in this business, in this business we make astrology real, because the whole mood and tenor of our operations are synced to which house Mars is in the sky. And the way it works is that the 26 months represents the time it takes for Mars and Earth to line up in their orbits as they go around the sun. Okay, and the Mars year is a little under 2 years. The Earth year is 1 year, but they're going in the same direction, so they cross. They cross over every 26 months, and so that means there's an optimal time. Is an optimal window to go from Earth to Mars. And I like to think of it as like changing lanes on the highway. You're not actually going zoom out to Mars. What you're doing is you're jumping off, you're changing your orbit slightly into a more elliptical orbit from Earth that will intersect the orbit of Mars And if you do it right, it will intersect the orbit of Mars exactly when Mars is there. Okay, that's the key point. You don't want to get to Mars before or after, and that's why we have a narrow launch window. It takes about 6 or 7 months if you do it right, and you leave before Mars is at opposition. In other words, before Mars is at its brightest in the sky. Opposition is an old term which refers to the fact that when Mars is really bright in the sky, or any planet for that matter, outer planet, it's on the opposite side of the Earth as the sun. Okay, so it's opposition. So you leave a few months before opposition, you arrive a few months after opposition, and you can be pretty sure if you look up in the sky and Mars is super bright in the middle of the night that there's a spacecraft somewhere on its way there. Okay, that's been true for many, many years. This past opportunity, it was United Arab Emirates, the Chinese, and of course NASA. NASA pretty much sends something every time to Mars. So there's this flurry, there's this little traffic jam, this little rush hour of spacecraft that takes off every 26 months. Now it turns out, there's been a lot of thought about how you come back, and exactly the same logic obtains coming back. That you have to jump off of Mars and intersect the orbit of Earth exactly when Earth arrives, and that also takes about 6 months. But from the time you arrive in Mars until you go all the way around from there to here is about a year and a half. So if any of your grandkids or great grandkids, end up going to Mars, you can pretty much count on it being a 2.5 year trip, unless we really make a lot of progress on very fast and powerful rockets that can do it the hard way. Because if you have enough power, you can pretty much do whatever you want. This is the low energy way to go to Mars. 2.5 years, 1.5 years on the surface, and a 26-month cycle. So it turns out that cycle is what's critical. And this was recognized, again, back to the Willy Ley and Wernher von Braun days, if not before. There's been hundreds and hundreds and hundreds of studies that's saying, well, we can take advantage of this. This is a risk-averse business, surprisingly, considering, all the space cowboys just say, just give me a rocket and a steering wheel and let me go. But it's a risk-averse business, and we would like to be able to bring people home reliably before we send them to Mars. And one thing that means is having facilities, having infrastructure in place before you even send the team. That's really the key. Having infrastructure in place before you send the crew. So the basic idea is you take one opportunity and you send your infrastructure. And then 26 months later, you send the crew. And that gives you, if you're allowing 6 months for the infrastructure to get there, or 6 or 7 months, so that gives you, up to about a year and a half to do any setup you need to do, and still give, the thumbs up to the crew. Okay, we're good to go. Go ahead and launch. That's the basic schema that has always been followed. It's not necessarily NASA's plan today, but it will be tomorrow if it's not today. And so what do you do in that 18 months? It doesn't take that long to set up your power plant, and to set up your habitat, and to set up your rovers, and to set up your anything you need to do to set up the return vehicle. But there's another opportunity to do something with that time, and that's to work to alleviate the burden of what you have to send in the human mission. As I wrote here, you need a way to get down to the surface. It might be a vehicle that goes down and comes back up. You need the crew, and you need their personal effects. And you shouldn't need a lot more to go, because everything should be waiting there for them. The camps should be set up, ready to go. The power plant is key. That's something like 25 to 30 kilowatts. That's a whole other talk. Because right now, what we've got running on Mars on that great big Perseverance rover, the size of a small car, is about 100 watts. Right? It's a light bulb. I think everyone here remembers 100-watt light bulbs back in the day when they were incandescent. That's what's driving that whole rover. For the human habitat, we need 25 to 30 kilowatts. So in the meantime, you've got the 25 to 30 kilowatt power plant just sitting there for a year and a half, not doing anything. And there's something really valuable you can do with it, which is to use it to make about up to 30 tons of oxygen, which you need not so much for breathing. That's just a couple of tons. That's hardly worth doing. You might as well bring that with you. But you mostly need for that rocket that's going to return to Earth. And if you do that, to take 25 tons of oxygen with you to Mars, means taking 11 or 12 times that into Earth orbit, which itself means a tremendous amount of fuel and effort. And it's going to be so prohibitively complicated and expensive to bring that huge tank of dumb old oxygen with you. That the way I always think of it is if we can make it there, we're going to advance the date of actually doing this by at least a decade. And so that's what we're all about. So just to elaborate on that, I bet most of you are familiar with The Martian, and a lot of you have read it, Andy Weir's book. And they talk about the oxygenator. And I was very grateful because all I have to do is tell, the right audience, hey, we're building an oxygenator and we sent it to Mars. So they understand what I mean. But the point is that anything that, quote unquote, burns fuel, that uses fuel for energy, needs to breathe, with almost no exception. There are monoprops and things, but basically you react fuel with an oxidizer, and by far the most common oxidizer is oxygen, because we live on a planet where oxygen is free and we never have to think about it. And in particular, what we never think about is that oxygen weighs more than the fuel it's burning, a lot more, several times more. So if you put a kilogram of gas in your car, you're burning several kilograms of oxygen, which you just pull out of the air. You guys remember carburetors, right? You just pull out of the air and get it for free and don't think about it. If you go into space, you need to take that oxygen with you, and it's a much bigger burden by a factor of several than the fuel itself. And so what breathes? Well, we breathe. Why do we breathe? Because we consume fuel. We call it lunch, but we consume fuel. And we breathe to be able to react that fuel and turn it into energy, as does a car, an airplane, a fire, and as does a rocket. And the only difference between the rocket and these other things is the rocket has to take the oxygen with it, especially that oxygen coming out from the ground. So how much oxygen does a rocket need versus how much a crew of four to six need over a year and a half? Well, you can kind of figure that out by thinking about the size of the fuel tank. And if you can picture the size of a fuel tank this rocket's going to need, to get back to space, it's going to be, 7 tons of fuel. That's a hell of a lot more fuel than what 4 astronauts are eating over a year and a half. Okay, so that's why the astronauts only need a couple of tons of oxygen, but that rocket that's going to take them back to space is going to need 25 tons. Okay, so that's the background of what we're trying to do here. And I should pause if there's any questions about that background.
A general question about Andy Weir's book, without getting into the details. How accurate is the stuff in the book?
He does a really good job. There's a certain amount of different people pick on different things. There are I know there are people that are concerned about the fact that no, you don't have like a hurricane that's going to blow over a rocket on Mars, which and that's the most egregious thing he does in there that's wrong is really talking about the effect of what the weather is really like on Mars, and the movie is way worse. But on the other hand, it turns out that the reason you won't have winds that will knock over a rocket on Mars is actually subtle enough that I call it artistic license. It's not because, because again, gravity's low. It doesn't take as much to knock over a rocket, and the winds tend to blow 4 or 5 times faster, even though the air is thinner. So all that's fine. The real reason is they don't have oceans on Mars. And if you don't have oceans, you don't get hurricane-like winds as you do on Earth. So that's subtle. What bugged me, for example, more so in the movie, was here's the worst case. There was a scene where Matt Damon, put a tarp over one of the exit doors, because the habitat had, blown up. He had blown up the habitat, and you saw the wind blows, and it actually inverts that tarp. And I looked at that and said, "My God, there's like 15 pounds per square inch or 10 pushing out on that tarp. That's a lot less likely than knocking over a rocket." Okay. So, and all the pelting with the little pebbles and stuff on the windows. And that bothered me because, I've grown to love this planet, and this planet that's full of blue clouds and pink skies and gentle breezes. And gentle breezes because the air is so thin and because there's no oceans. And when you portray it as these raging storms, in making this incredibly my nice gentle breezes on Mars into an incredibly hostile environment, that that hurt a little bit. Okay, but basically he does a fantastic job. Does that answer your question?
Sure. I don't like potatoes, of course.
Potatoes, well, okay. The other thing I could quibble on, and this is something I was intimately involved in back in the Phoenix mission. My team discovered that Mars is loaded with perchlorate, which is kind of toxic. It's reversible, but it goes right into your thyroid and causes hypothyroidism. And that's why we keep it out of our water system. So yeah, those potatoes probably would have been loaded with perchlorate if he was using Martian soil. But I'm getting kind of geeky now.
Ted has a question. Has his hand up.
Yeah. One of the issues that always comes up is the situation with respect to the solar radiation, and that you probably have to live underground for that year and a half. It didn't seem that that was included in your initial scenario. Is that still being ignored, or is that part of the thinking?
Well, I think there's a lot of gray in that argument. If you're a professional airline pilot, you get a lot of radiation exposure over your career. And that is how people tend to look at this, is what is our career exposure. The trip to Mars is not particularly worse than spending the year in the space station, as people do. The worst part is when you're in space. One way to think about it is that when you're on Mars, half the sky that you would see from space, half the sky is a planet, right? So there's no radiation coming up from below anymore. It's all what's coming down from the sky. We've studied the secondary radiation from the ground. We understand that. And there is an atmosphere that does block a lot of the low energy, the protons, the solar wind. And actually, that's not hard to block. So what you're worrying about is galactic cosmic rays.
Yeah, and it doesn't block those.
It doesn't block those.
You have no magnetic field to deflect them either.
Yeah, either a magnetic field or really like a couple of meters of water in some form. It can be done. Underground is a solution. It turns out, if you do an interesting thing that people don't talk about much, because is if you do the math, if you simply live in a pit, an open pit of some kind, which could be even a small crater, you knock the radiation way, way down, because most of the solid angle of the sky you're looking at is actually near the horizon. There's a lot more sky near the horizon than directly overhead. So if you're in a depression, you block most of that and you can cut the radiation way down. But the bottom line is that if you did nothing, it wouldn't be terrible. Okay, they wouldn't let you go more than once, but it is in, would exceed the OSHA limit, but not. Put it this way: as astronauts I've talked to about this have put it, this is not the biggest hazard of going to Mars. Right? You might get cancer a few years earlier when you get old. That's not what they worry about. So I think they'll ignore it. I personally have what most people consider a wacky idea. I consider it a very serious idea that we should be landing on the North Pole of Mars. And if you do that, then you basically live in an igloo, or you dig a pit with a chainsaw and you surround yourself with ice, and that takes care of the radiation. Um, that's only one of a number of reasons I think we ought to go there. But I can tell you that me and three other people in the world think we should, and three or four, and everyone else wants to go to the equator. So that ain't going to happen. But if it turned out to be more of a problem than we thought, it's a good solution.
Okay, Mike, let's let you proceed.
Okay, yeah, I get easily distracted. You've noticed that. This is just too much fun. Anyway, so there's this mission going to Mars, Perseverance. It's been there since February 2021, and it's a really unusual mission compared to anything else that NASA has sent to Mars in its breadth of interest. And I like to say it's a mission that's looking at today, tomorrow, and the day after tomorrow. So the today part is, it's got a whole bunch of instruments that are studying rocks. And the theme of those instruments, if you look at Pixel, if you look at Sherlock, if you look at SuperCam, is to do kind of chemical microscopy, if you will, in a way. In other words, not just to have a spectrometer that says, I see some crystalline structure that looks like it might be, sodium chloride or jarosite or something, but to actually be able to resolve that on, to map that on a fine scale, so we can say, and it's in this little crevice of this rock, or in this little, in the small grains of rocks, but not in the big grains of rocks. That's kind of the scientific bias, or theme of the instruments. That's today. But the real, thrust of the mission is to be the first leg of sample return to Earth, because, while we like to tout what all these amazing instruments can do, it's what I think of as junior high school science. It really is. Doing a junior high school science experiment on Mars, is a $100 million, risky adventure that might work. And it's pretty sophisticated junior high school science, but it just pales compared to what we could do in a real laboratory full of instruments. And so really all the scientists interested in the rocks and the air and the soil and, in life and any aspect of Mars are just drooling over the idea of having a little bit of it in their laboratory, as we do for the moon. And that's what this mission is truly about. Now, there are plans being made to return the samples that are being collected by Perseverance, and within a few weeks, we'll be putting down our first so-called cache of these hermetically sealed little core samples that we've been taking for the last year and a half. Okay, we've been acquiring, well, maybe the last year, we've been acquiring core samples, and we have a whole bunch of little tubes stashed in this rover that we've identified a site. We're going to put it down in a couple of weeks in this so-called contingency cache. And if all goes well I don't know what the current date is, but probably 2028, I think. There'll be a mission coming that will either rendezvous with Perseverance, okay, because we now expect these things to live for years, or we'll send out little helicopters to go pick up that cache, bring it back, return it to orbit, and send it back to Earth. And so we might get it back in a decade. And for a lot of us working in the mission, that's kind of beyond our retirement horizon. So we're investing in the future. We're investing in, that's the tomorrow part, and the bonanza of science that will occur when those come back. And then of course, you see, Ingenuity was kind of a surprise in this mission, and it's been a great success and is part of that sample return plan. But then with MOXIE, we're investing in the day after tomorrow, in the future, not in 10 years, but maybe in 20 years or 25 years when we send people to Mars. So the range of ambition of this mission in time is from, tomorrow to 25 years from now, and that's truly unique. MOXIE is an oddball here because it doesn't even, there's no reason this instrument needs to be in a rover. It could just be sitting stationary on the surface. It's not studying anything about Mars around it. It's purely technology demonstration. It's not funded and supported by the science directorate like everything else on here. It's funded and supported by the human exploration folks. So it's the oddball, and it's kind of a fun place to be. And I still get to enjoy all the great science going on. So let me back up. What is MOXIE? Okay, half an hour in and I haven't told you what MOXIE is. It's a scale model of that plant I've been talking about that oxygenator that's going to make 25 or 30 tons of oxygen someday. It's a scale model for a couple of reasons. One is that the rover isn't big enough for a full-scale model, which would be kind of the size of a washing machine. But more importantly, because the rover can make, as I mentioned, about 100 watts of power, and the full-scale instrument needs about 25 kilowatts. So that constrains what we can do, but lets us test all the principles and, just the, you don't know, it's just the test drive. You don't know what you're going to find until you go and do it. People always ask, why can't you do this in the lab? And the answer is because, lab experiments are doomed to succeed. They will always succeed. And when you actually try to put something in the field, it will fail for reasons you can't possibly anticipate. So it's kind of the unknown unknowns. So what's the scale model going to do? And I have to be careful with the word scale model because it's 1 to 100 to 200 in terms of production. That doesn't mean it's 1 to 200 in terms of size or particularly in terms of power. The power scales really, really badly. So it's much more power efficient. It would be a much more power efficient if we had sent a full scale system. We couldn't do it because we don't have the power. But anyway, it's going to make 6 to 10 grams of propellant grade or breathing grade oxygen. They're the same thing per hour from the Martian atmosphere. And what is that? That's about, each of you sitting there are probably breathing about 20 grams an hour unless you're working out in your Peloton while you're watching, in which case you might be burning 30 or 40. So this isn't even enough to keep one of us alive. It would keep a small dog alive. It's also about what a tree would put out, which tells you that the level of production we need for that future system is like a couple of hundred trees. It's like sending a pretty good orchard, to Mars. And we'd much rather send something the size of a washing machine that doesn't need to be watered. So that's the idea. That's what MOXIE is. It's a tech demo. It's a test drive, if you will, and scaling it up 200 times actually would have been easier to build at full scale than to try to build a miniature. But we did what we had to do. So that's what MOXIE is. The name, I got to choose the name, which was great because I had just come to Haystack Observatory back from returning home from California, a year or two before that, and really wanted to capture some local color. And I'm sure all of you remember this stuff. It's still available, but they don't claim that it stops the appetite for intoxicants in old drunkards and insanity and blindness, etc. But I do like the fact that it makes you able to stand twice the usual amount of labor with less fatigue, because that's something we sure could have used when we were building this thing. Anyway, I got that Ted Williams poster behind me, but that's MOXIE. But this is the MOXIE we're talking about, the Mars Oxygen ISRU experiment.
Mike, can you still buy MOXIE in the grocery store?
You sure can. Now the trick will be you can buy it in cans, and it's you have to look a bit harder to find it in the classic bottles. I realize I have my video on, so I don't think I can show you one. But someone told me Cracker Barrel had them in the original bottles, and let's see if we can make that show. If I hold it close enough to me, yeah, there we go. All right, there's your MOXIE bottle. I said my office is a mess. That's why you're getting Chesley Bonestall in the background. Um, all right. So what do we got here? How do you turn CO2 into oxygen? Well, first of all, I don't think I've said anything about CO2 yet. What is that Martian atmosphere that Andy Weir and the movie so badly maligned? Okay, it's almost entirely carbon dioxide because that's what you tend to get on planets, or on Earth-like planets. And the only reason we have all this oxygen on Earth, well, it's basically a pollutant. That all this early biology, the early life on Earth, consumed good, healthy, wholesome carbon dioxide, just like trees and plants do, and turned it into oxygen, which is their waste product. And they did that so well that after a while, CO2 became extremely scarce, and oxygen had polluted the entire planet to the point that we had to evolve new types of life that actually could use this stuff, and that's us. So lacking that history, planets like Mars tend to have only carbon dioxide in the atmosphere. Mars being a smaller planet and not protected by magnetic fields, that turns out to be important, tends to lose that carbon dioxide at a much faster rate than we lose our atmosphere here on Earth. So by now, the atmosphere is very thin, about less than 1%, maybe 0.5%, as thick as it is on Earth, and it is almost entirely carbon dioxide, over 95% carbon dioxide. So that's what you got, and we want to make oxygen out of thin air, okay? Thin Martian air, which is almost entirely CO2 with some inerts, with argon and nitrogen mixed in. Fortunately, we have that technology. And you hope not to send something to Mars starting totally from scratch. You hope to have some technology capability. And in this case, we do. We have something called solid oxide electrolysis, which is the kind of technique of choice for fuel cells and electrolysis cells that deal with large quantities of things. And in particular with oxygen, that's about the only mature game in town is solid oxide electrolysis. If you're getting into hydrogen fuel cells, often these are low temperature, so-called proton exchange membranes. They're plastic or polymer membranes. But even for hydrogen production, for cars or hydrogen economy, they're back to solid oxide electrolysis, and anything involving carbon dioxide, including the oxygen sensors in your car engines, use the solid oxide technology. So what is this? It's an electrolysis. First of all, electrolysis and fuel cells, you notice I'm using interchangeably. They're the same thing run in opposite directions. Okay, so in a fuel cell, let me give hydrogen as an example because it's easier to identify with. A hydrogen fuel cell, you put hydrogen in, you put oxygen in, it reacts, it burns, if you will, but and what it puts out is electrical current, is electrons. So you get hydrogen in, oxygen in, water out, electricity out. That's a fuel cell. Same thing with carbon dioxide. You put in carbon monoxide. You never want to use carbon. Just stay away from carbon. It's bad stuff. Carbon monoxide, you put in oxygen, it reacts, you get CO2, you get electrons out, electricity out. You run it backwards, it's now an electrolysis system, and you do just the opposite. So you start with water, you put electricity in, you get hydrogen and oxygen out. And you can buy systems like this for even powering things like drones, where you put in water and plug it in the wall, and it charges up the little hydrogen and oxygen reservoirs. Then you clip it onto your drone, and it burns the hydrogen and oxygen in the fuel cell and powers the drone. This is yin and yang. They go together. The funny thing on Earth is if we do this process with CO2 going to CO plus O, we would throw away the oxygen because we don't need it, and we would keep the carbon monoxide as an element of something like syngas or some other clean fuel. So we have some art on Earth. What's involved here is a high temperature, like 800 degrees C, a ceramic membrane. It's a zirconia, actually, an yttrium stabilized zirconia in this case. That's what the YSE is. It's got a perovskite electrode on the well, the definition of cathode and anode switch whether you're doing electrolysis or fuel cells. But for electrolysis, on the anode side, it's got this perovskite here, this porous positive electrode, and then it's got basically a nickel foam or a nickel felt, on the anode side. And the purpose of this is to take carbon dioxide. It's very hot. It's loaded with catalysts. It has electrical current across it. And that's all those three things combined are enough to split those CO2 molecules into 2CO and 2O2, two oxygen, so O2 minus, two oxygen ions, doubly charged oxygen ions. And what happens is that the voltage, this membrane, this ceramic membrane at high temperature has the unique property that the only thing that can pass through it, is oxygen ions. And that's the key to many electrolysis, if even a pH meter, that's the key to many electrolysis systems or batteries or whatever, is having these selective membranes that only pass one type of ion. Now, even under current, under voltage, if you pull two doubly charged oxygen ions through the membrane from one side to the other, you're going to have a charge imbalance, which is then made up for sending 4 electrons in the other direction. And that creates neutrality, that closes the circuit. And that's why, again, yin and yang with this, you have ions going one way and electrical current going the other. And one direction is fuel cells, one direction is electrolysis. Okay, so that's how this thing works. And given the limitations of wanting to do this reaction and not produce carbon, which would gunk up the works very badly, there's only so much oxygen you can create per square centimeter of this stuff. So what you need to do is maximize the surface area, and the way that is typically done is by making individual cells and stacking them up back to back, so they share these it's called an interconnect, which has nickel on one side and perovskite on the other side, and then you put the next cell down. And so you make a multi-decker sandwich like this, connect wires across it, and pump the gases in and out. And that's how you do it. That's how you turn CO2 to carbon monoxide and oxygen. So in practice, you make something that looks like this. That's maybe about the size of my mouse.
Mike,
yep.
We have a question here.
Where did
Go
you
ahead.
get 800 degrees Celsius from?
Sorry?
The question is, where do you get the 800 degrees Celsius from?
Yeah, good timing of that question. So excellent timing. So you take this little gadget and you have to package it. So this was built by a company that was at the time called Ceramitech, which was part of the Coors empire. I don't know how many of you are aware that Coors is a titan in the precision ceramic business. They split that off into a company called Coors Tech. The company that made this has since then gone, split off into a small business called Oxyon Energy. But JPL took that and had to package it because there's three issues involved. One is you have to heat it up, okay? And that's actually not difficult. They use, see these metal things here, if you can see my pointer, those are kind of metal, what we call heater carriers that really just have little strip electrical heaters in them. And the idea is for it to kind of to make a makeshift oven. It's not a great oven, it's a makeshift oven that just brute force uses electricity to create heat, to drive the heat into these cells. And a fraction of that heat actually goes into making the oxygen. And that's another story because it's an endothermic reaction. But then once you have this hot and we have a very limited power supply, you don't want to lose any of that heat. In principle, you can heat something to 800 C and have it consume no energy at all if it's perfectly insulated, like your thermos bottle. So that's what all this black stuff is. And then these open areas are filled with aerogel. But let me talk about the black stuff. So the other thing it turns out just pragmatically you need to do in these cells is you need to squeeze on them to get good electrical contact to keep them mechanically stable, you need to squeeze on them with a lot of force. And that turned out to be a real engineering challenge. We don't care so much on Earth if these things leak, so they don't worry about it so much. But for a package from Mars, this was a real challenge because you now have to squeeze on this thing with strong springs. And since it's at 800 degrees C, you can't practically put the springs inside the hot zone, which would be the easy way. Inconel can kind of do it up there, but you don't want to take a risk. So you want to squeeze on it from the outside, which is what these springs are doing. But now you're squeezing on insulation, okay? And that's where things get really dicey because, most of these, if you ever held aerogel, for example, you can crush it between your fingers. So to come up with something that is truly insulating, but can withstand, the force of these springs squeezing it with very high pressure is tough. And the product used is something called Min-K. And the Min-K is pre-compressed because it will compress to some extent. And they finally came up with a system that included the needed insulation and supported the spring force, and it all got packaged into this box, which is about, now we've gone something from the size of my mouse to the size of, something, about, now where am I? I'm going to hit wrong way. About this big, just to provide all that packaging. That's this gold box here because JPL loves coating things in gold. They claim it's for thermal properties, but I think they just like coating things in gold. I actually asked the project manager because I don't like putting gold on aluminum. That's my whole background in sort of surface science because it makes a really nasty alloy if you don't have a good interlayer. And so I asked him, Jeff, why did you coat this whole thing in gold? And he looked at me with a totally straight face. And this is not a guy that has a lot of sense of humor. And he said, Mike, if we had made it out of solid gold, it would have just been too heavy. So that's JPL for you. The device next to it is kind of the unsung hero of this whole system. Because everyone focuses on number one, on this piece here. Then there are all the engineers that have to worry about number two as being the daunting problem. But number three here, you got to pull in all that carbon dioxide from somewhere. Just like any system you have, your HVAC system in your home, it's somewhere or other there's a fan and a vent that's drawing the air in. And when the air is thin, that has to be a pretty powerful draw. And so that you don't have huge pipes and tubes, it's got to compress the air as well. And so what we have here is a compressor. It's a very simple thing. It's what's called a scroll compressor. You probably have these in your car running your air conditioner. But like anything else, to make it work on Mars was a heroic undertaking. And a company called Air Squared figured out how to make these little scroll pumps, scroll compressors that feed the CO2 into the system. You put the whole thing together, it's about, yay big. And 20, 30, 25, 30 centimeters on a side. You combine it with a bulletproof electronics box, bulletproof in the sense that it does not fail because we can't go up and fix it. There's a lot of plumbing that's involved. What you're looking at here is early in assembly. By the time this is done, it's a massive spaghetti. But when you're done, all done, it looks like this box here being loaded into the rover. That's the finished MOXIE. I won't go into this diagram. Really, all this is showing is that operating this thing is a matter of staying in a sweet spot of having the right voltage and the right fraction of carbon dioxide to carbon monoxide in the gas going through this thing. So if you try to get greedy and make too much oxygen, if you try to push it up where it's mostly carbon monoxide in the gas stream, your voltage window of operation kind of goes away. So finding a happy medium in here when you really don't quite know exactly where you are, it's not smart enough to kind of dynamically adjust this, and you don't know that you've crossed that line and started making carbon until it's too late. So this has been the real challenge here is staying in that operational sweet spot by adjusting the voltage and adjusting the compressor speed, so that we can make a good amount of oxygen without risking, making carbon. That's what this diagram is all about. But let's get down to more of the basics of running on Mars. There again, there's this picture on the lower right, safe arrival, and the video that you can find
Mike,
online.
we have a
Go ahead.
question
Yeah.
here.
Yeah.
A quick question, going back to your previous slide. I've always wondered why you pick carbon dioxide rather than some other oxygen-containing compound there. Is it because it's a gas and nothing else is a gas, or are there other compounds that you could have used and perhaps, well, you've had to go on a different route to get the oxygen out. But I'm just wondering why CO2 was picked rather than some other oxygen compound.
Yeah, no, I'm glad you asked that 'cause I did kind of gloss through that pretty quickly. And it's an important point. The important point is what you want to start with is your raw material. You know, if I look out the window, I see lots of trees, and those trees pull carbon dioxide out of the air because they're not terribly mobile, right? They can't go and find their food, so they pull carbon dioxide out because it's all around us, and they pull oxygen, they pull water up from the ground because we live on a soggy planet, and that's how the trees work. They pull in carbon dioxide, they pull water up from the ground, they make carbohydrates, they make oxygen. We have the same situation on Mars. The atmosphere is over 95% carbon dioxide, and the rest of it doesn't contain oxygen. So if we want to use the air as the feedstock and be like a tree, that's all we have is carbon dioxide. There's no other choice. If you want to start using soil or rocks as a feedstock, that's what you have to do on the moon. Okay, I mean, this almost any rock you pick up off the ground has lots of oxygen in it. You know, silica, sand, lots of oxygen. But you have to dig it up. You have to melt it. You have to process it. You can do it also galvanically, electrochemically. But it's understandably a whole different level of robotics to do that task. Again, on the moon, we have no choice. But on Mars, conveniently, there's this carbon dioxide atmosphere all around us, and we can just be like a mechanical tree and take what's available. You know, so basically, you know, finding food and resources for if you're an animal, if you're a plant, or whatever, is some combination of, you know, how well they work and how available they are, and how much work you have to do to extract them. And in case of you know,
Right,
most of the
also-
life on Earth, you just grab what's floating by in the atmosphere.
We have another question.
Yeah,
Go
is
for it.
anybody trying this out for the moon? Something like, you know, using the soil, getting oxygen.
So-
making
Oh yeah,
oxygen.
people are working on this for the moon, but not from. There's no air, of course, so there's no carbon dioxide. So for the moon, people are developing, you know, sort of molten rock solutions to pull out oxygen and other materials. And then there's the folks who've been watching too many episodes of For All Mankind, who are convinced that we're going to find, you know, chunks of ice in the South Aitken Basin on the South Pole, and we're going to mine that ice, and we're going to have water to start with. And if you have water, this gets easy also. And on Mars, you know, there's lots of water on Mars in the form of ice. It's yeah, it's one of the reasons I mentioned I'd like to go to the poles because there's lots of water there, lots of ice there. Even near the equator, there's deposits of ice underground you could conceivably mine. And I think it will not be too far in the future after we start sending regular crews to Mars to you know, to kind of man a research station, that we will have access to water. In the short term, we won't. So that's what's going on for the moon, but nothing nearly this mature. That answer the question?
Thanks.
Thanks.
So let me try to kind of race through.
Mike,
Go. Yeah, go ahead.
yeah, you mentioned the perchlorate. That's the oxidizer for solid fuel rockets.
Yep.
And there's
absolutely
a
right.
lot of oxygen in that.
Yep.
But that was never considered to be a viable candidate for this process.
Only by me.
Well,
I'm a voice in the wilderness. Well, look, I can tell you, I mean, there's a couple of reasons that are good reasons. One is, again, while it is ubiquitous in say in the soil, what I call the soil, You can't use that word around real soil scientists because they'll tell you that soil has organic life in it. But the regolith, there's lots of perchlorate in all the loose granular material in the regolith, but you'd have to have robotics to dig it up. You'd have to be able to extract it, which is not difficult, but it's kind of like making espresso. You know, you can extract it with water or steam and then recovering the water. It's a process. It's a heck of a lot harder than just breathing in. The other problem with it, with perchlorate, once you've accumulated the perchlorate, is yeah, you can make solid rocket boosters, you can make oxygen candles, you can make 4th of July blue fireworks out of perchlorate, but it has this characteristic that it is actually incredibly stable stuff. And the only way you can get energy out of it is to heat it up over 200 degrees, at which point it explodes. And that's why you make all these things like fireworks and oxygen candles and solid rocket boosters out of it. If you want to use it as a source for continuous stable energy, that's really hard. It doesn't like to do that. It likes to explode. The only process I know of for doing that is a really intriguing one. Because while people haven't managed to figure out how to gracefully get power out of perchlorate, microbes have. Okay, microbes have, and there's at least one case I know of where someone built a microbial fuel cell, where you have just a colony of microbes in a vat of chicken soup or whatever nutrient, and they sit there and consume perchlorate and put energy out. And this was done not so much as a source of energy, but as a way to remediate the perchlorate contamination in water. And that was what it was developed for. And hey, by the way, we can get electricity out of it. So, there are pathways to use that perchlorate. I think more likely that someday, again, when we have a permanently occupied base on Mars, maybe we'll be making solid rocket boosters to power rockets into space. I totally agree. That's an excellent idea, but it requires a manufacturing infrastructure that we just are not going to do robotically. Anyway, we landed on Mars on February 18th, and go look at the video sometime. It's because there's never been a spacecraft like this that has been instrumented with lots of cameras to document its own landing. All we've ever seen before are simulations and waiting, and finally we get a confirmation, yes, they're on the ground, and then you take pictures. Anyway, it was just, for those of us who've been in the business for decades, I can't tell you what a thrill this was to actually watch our rover land. Okay, I mean, just think about that. Who's taking the movie? And we got to do it this time. It was amazing. All these streaks you see down here are actually, it's a movie, and that's the dust blowing around from the rockets. It's just super cool. So let me talk a little bit about MOXIE. What does a MOXIE run look like? First of all, we run every month or two because this rover is just bristling with instruments and they're all competing for time. It turns out it takes us, a week or two to figure out what we've done and what the results were, and a week or two to kind of plan the next run. So running once a month or every couple of months is plenty for us to learn what we need to learn. And the other problem is that MOXIE is very power hungry for this little rover, and the rover has batteries, so we're not limited to 100 watts. We can run at a few hundred watts until the battery runs down to its safe level. So here's what we have to do. The first thing we have to do is something that makes people turn pale that are in the business. It's something that you should never, ever do with a solid oxide fuel cell or a solid oxide electrolysis system. And that's to let it cool down and then heat it up again. That's a sure way to break it. Generally, when you have a solid oxide system running at 800 degrees C, you just leave it hot all the time. We can't obviously do that. We don't have the power. So every time we run, we have to turn it on and heat it up to 800 degrees C. That uses a lot of power, and that takes a couple of hours to do it and stabilize it. And that was the most difficult part of the development of this thing, was coming up with a material system that was robust to repeated cycling. Okay, so we do that for a couple of hours, And then what we get to basically adjust, it comes down to the knobs we have are the voltage, which determines the current. So we can run a feedback loop at constant current, which we've generally done. We can adjust the compressor speed, which tells you how much air you're drawing in. We can adjust the temperature, which we seldom do. We usually let it just sit at 800 C because there's also kind of a sweet spot. If it gets much hotter than that, it can do damage. So those are our three knobs, and we spend about an hour doing experiments after we're warmed up, meaning making oxygen in different modes, and by turning those three knobs in combinations thereof. So that's our few hours, and then in the meantime, nothing else is going on in the rover because we're using up all the power. So it's when all the people running the other instruments get to, take to knock off for a day, and if it's, in the summertime, go to the beach or whatever they do, just R&R. So that's what a MOXIE run looks like. And, I wish there were cool videos to show of oxygen coming out and, burning in a flame or so. I wanted to do that, actually, was to burn the product. But NASA didn't look at that very kindly. So all I can do is show you a plot of oxygen production. We warm up, we make oxygen. This is the cumulative total. It has little wiggles in it because we're not always making it at the same rate as we do our little experiments. And we make 5 or 6 or 7 or 8 or 9 or 10 grams, depending what we're doing. And then we stop. I mean, it's kind of not very exciting on the face of it, but I can tell you it was pretty damned exciting when we saw it for the first time. So when I talk about experiments, what is it we're doing? Well, we're trying to really test, the ultimate goal, two ultimate goals. One is to test whether this thing is reliable and rugged and robust enough to trust a human mission to it. Okay. The other is to learn as much as we can about it to inform the design of that future full-scale system. So there's some combination of just putting it through its paces to test its ruggedness for running 24.5/7. The Martian day is a little longer than our day, so it's 24.5 or so. And the other part is to learn about it. So in terms of the first part, one of the key things that varies with season, there's dust seasons on Mars, but other than that, one of the key things that varies is actually the density of the atmosphere. I mean, this varies on Earth too. You have high pressure fronts coming in, you have the temperature changing, and we all know there are, all of us here in New England since Deflategate understand the ideal gas law, that was an amazingly educational little football brouhaha, and everyone knows the ideal gas law. When you change pressure, when you change temperature, they go together proportionally, and together they make density. So the air density is changing on Earth a little bit, but on Mars it changes hugely. The pressure itself over the course of the year, the atmospheric pressure can change by as much as 30% in late northern and southern winter compared to other times of the year. And then the temperature, even day to day, can change by 80 or 90 degrees centigrade, which is a huge daily swing. And there's also a daily pressure swing. So what you're looking at here is the Martian year. And this is actually models, because they're kind of Monte Carlo type models, so they have all this noise in them. But the model isn't precise any more than a weather model on Earth is precise, because Mars has weather. But more or less, the density of the air is going to have peaks and valleys. This is the nighttime on top because it's colder at night, and therefore the air is denser. This is the daytime extreme on the bottom, where it's warmer and less dense. And then the seasonal variation, and you can see from the very top here to the very bottom, is about almost a factor of 2, almost. And obviously, the amount of oxygen we can take in with our compressor the amount of carbon dioxide affects how much oxygen we can make on the other end, all right? So that has a significant impact on how we operate. So we thought, all right, we're going to try to span the day-night variations and span the season with our, operations every month or two. And we had a deal with NASA that we would basically run at least 10 times. So we mapped out our 10 runs, just notionally saying we'll try to cover these cycles, and then we're right now we're around here, and I don't know if I updated this right, and we're just getting into dust season, and dust can obviously have some impact as well. So this is what we actually did. We're now close to Sol 600. What Sol are we today? We're in Sol. Oh my goodness, 598 today. That's going to be Sol 600 in a couple of days. And a Sol is a Martian day. It's a little longer than an Earth day. So, okay, so what we actually did here, I seem to have lost it, is we've run 11 times. These numbers, FM means this is the flight model, because we also have an engineering model we run back on Earth and something called a flat sat in our laboratory. OC is the operational cycle. We track the heating and cooling cycles, whether or not we make oxygen, because that's what determines the aging of the instrument. And the first one we did on Mars was number 9, because we had cycled this thing 8 times in testing. And so we've gone from 9 to 19, and both some low density runs and most of them in the nighttime. And the ones marked with asterisks were not so much for the purpose of mapping out the cycle as for doing other kinds of experiments that to allow us to study things on the instrument. The ones that don't have asterisks are just, let's follow the extremes. So overall, we've made 11 runs. We've made 83 grams of oxygen, which would keep one of us alive for maybe 4 hours. You guys can choose who that would be. And we've run for about 860 total minutes, so a dozen plus hours. The last time we ran, we took advantage of being way up here in the density, and we kind of set a record of 10.4 grams per hour. We did it tentatively. The trouble with pushing the limit to make more oxygen is you risk making carbon. So we ran for a long time, even at 9.6, which is quite high, to make sure we didn't damage anything by our little brief foray to 10.4. We didn't, and so the next time we run, we're going to try to do a long run at 10.4. To put that in some perspective, our requirement was 6, and our goal was 8. So we're already significantly exceeding our goal in oxygen production, and that's kind of our thing right at the moment is let's see how far we can push these systems without taking undue risk. And that's what's going on. So I mentioned the fact that cycling is a killer on these instruments. But another way to look at it is it's kind of an accelerated aging experiment. When we really run the instrument, the full-scale instrument, what we're going to have to do is run it for months and months and months, day and night. And we will study in the laboratory how it ages over time. But we know that when we cycle it, we accelerate that aging. We age faster. The mechanisms are similar. They just happen a lot faster. So we've been tracking the aging of the instrument over time, and using something called the intrinsic area-specific resistance. So basically, this thing acts like a diode. You guys are electronics people. It's a certain threshold. It starts turning voltage into current. So it has a diode-like current-voltage relationship. And you take that linear portion and you look at the slope of it and you treat it as a resistance. Okay, so that's the area-specific resistance. Area-specific is that it's a resistance per square centimeter. And intrinsic means we found a way to make a few corrections to that calculation so that no matter what current you're running, or no matter what pressure of gas you're running, you'll get a common number. And it has to do with integrating from one end of the cell to the other. So we have this figure of merit, and we track it over time. And it looks like it's changed a lot over the 11 runs, but if you actually look at the numbers, it's changed from 0.95 to 1. It's a very small change. To give you an idea, this little line here is equivalent to about 10 millivolts per cell. And whenever we run, we allow an error margin of at least 100 millivolts. So we're barely cutting into our error margin with the degradation over 11 runs. And I think the message from this is that we can run for dozens more runs before we even need to start kind of cutting back on our production goals. So that's really, really good news. This is really exciting news. And we've also looked at purity, oxygen purity, and what we learned in hindsight was very little surprise. We have the ability, by controlling the rate at which oxygen is produced, that's controlling the voltage, and by controlling the amount of gas flowing through it, that's the rate at which we spin the motor on the compressor, we can change the relative pressure between the cathode and the anode, between the CO2 side and the oxygen side. And when the CO2 pressure is higher than the oxygen pressure, some of the CO2 actually does leak into the oxygen. When we fix it so the CO2 pressure is lower than the oxygen pressure, we can have no measurable CO2 leaking into the oxygen. And again, when I say it that way, it seems obvious. It wasn't at the time. We pretty much learned this on Mars. So what we showed is as long as we design these systems so they keep a little bit of overpressure on the oxygen side, we can guarantee you 100% purity, or as close to it as we can measure. Just for reference, 99.6% in the middle here is kind of the standard for breathing oxygen or propellant grade oxygen. So we can check that box and say we learned something about how to do it, but we can certainly say that we can make pure oxygen this way. So that was a big success. Experiments. It turned out there are some things that we would have liked to have known before we launched, but we didn't know that we needed to know until we got experience running this thing. And part of it is the various resistances on the wires themselves, because the wires are not good conductors. They're not good copper wires like you would do in electronics. They tend to be Inconel wires because copper would melt. And Inconel is not anywhere near as good a conductor of electricity. And they tend to be very fine wires because you don't want heat leaks. So you need your wires to be as fine as possible. That means the resistances are relatively high. As you can see, hundreds of milliohms, these red numbers that we've been mapping out for all the key resistances in the systems. And if you consider the fact that we're running, maybe we split this electrically into two half stacks. Each one runs about 6 volts, and we're running 2 or 3 amps. So the equivalent resistance of these stacks is only 2 or 3 ohms. So you start getting an additional 10% resistance in these wires. And to do the kind of precision control we need and to measure these, get these figures of merit, we need to know these numbers very precisely. We just didn't know them. So we had to come up with very diabolical experiments that would allow us to figure out those resistances with the instrument on Mars. And we've done that. So that was just an example of a type of experiment we've done. It's almost embarrassing to explain. Because you say, why the hell didn't you just measure it before you launched? We didn't know. So as an example, normally I showed you those 2 half stacks. We normally run the same current through both of them. If we run a different current through both of them, it turns out they're wired so they have a common middle lead, that is connected with opposite signs of current, so the current zeroes itself out. So we really only have current flowing through the top and bottom lead normally, which means we only get a voltage drop across the top and bottom lead, not across the middle lead. But if we intentionally unbalance these stacks and we run more current through one than the other, we suddenly turn on the voltage drop across the middle lead, and we can use that to determine the resistance. So whether you followed that or not, the idea is you can do experiments like this to figure out those resistances. What are we doing currently? The most recent thing we did was voltage control. The instrument was designed for a kind of a curious reason, to have a feedback loop to keep the current constant. The curious reason is the fact that the current, I mentioned 4 electrons per oxygen molecule. So the current controls the amount of oxygen you produce. And if you run at 2 amps, you're going to get 6 grams of oxygen an hour. Almost exactly, as it turns out. And the requirement was to produce 6 grams of oxygen per hour. So all the development was done with this current control loop in effect, running at 2 amps to show we could get 6 grams per hour. Unfortunately, where you get into trouble and start producing carbon in particular is when the voltage gets too high, has nothing to do with the current. So for safety purposes, you'd rather fix the voltage and turn off that current control loop entirely and let the current do whatever it wants to do. But we had never done that before. It had never been done on Earth. So we had to do experiments on Earth to show that that works. It turns out that current and control loop lag is rather long. It's 3 or 4 minutes. So it was kind of eye-popping what we saw in the relationship between current and voltage when we turned the loop off. And you can see we keep, in this run, we designed lots of ups and downs of current voltage because we could, right? We were playing. And to see what would happen. And you can see that instead of those sort of slow rolls we're used to seeing that look more like this, we were seeing all these very, very sharp transitions in voltage and current, which is very cool because now we can start to see other things going on, like the fact that when you change the current, the gas pressure in the anode changes. That doesn't happen instantly, and we can actually see that happening. We can never see it before. So that's, again, another, just to give you another flavor for the kind of experiments we're doing. We're going to try to turn on pressure feedback so we can control the pressure in the cathode by changing the motor speed on the compressor in a feedback loop. That's never been tested on the ground either, but the software is there. So that's the kind of stuff we're doing. Anyway, let me move on. Anyone can find MOXIE data, like every instrument on any NASA mission. It's made public as quickly as possible by kind of, the rule is it must be within 6 months of being acquired. But it's all available on what's called the Planetary Data System. And they have different nodes for different types of experiments. They put us in the atmospheres node because they didn't know what else to do with us. So anyway, that's where you could find the data with all the explanatory material telling you how to use it. One more little data tidbit I'll throw out at you. If a lot of the purpose of this instrument is to figure out, how robust MOXIE is and how well it works, how do you monitor how well a compressor is working? I mean, anyone that's ever worked with these instruments or worked on your car, for God's sakes, knows the answer to that. You listen to it, right? And if it sounds funny, that's the first indication something is wrong. Well, it turns out there are a couple of microphones on this rover. This is the first time we've ever done that successfully. And there's one of them on top of a mast far away from MOXIE, so we can be pretty sure that the sound is traveling through that thin Martian air. And we've turned on that microphone every time we make a transition. Either we turn MOXIE on for the first time, or we're making a change in the speed of the motor. And what we see is also kind of eye-popping. You're looking at spectrograms here. So it's time going from left to right, and frequency from about 0 to 1 kilohertz going from the bottom to the top. The motor is spinning at about, and this has had some processing, by the way, on it to remove some of the noise. The motor's spinning at between 30 and 50 hertz. So when the motor turns on, this first little line way down at the bottom is actually the speed of motor rotation. All these other lines are harmonics. So you get a line at 30 hertz, at 60 hertz, at 90 hertz. And there's a lot of them that you can see. These two lines were on even before MOXIE turned on. Those turned out to be pumps on the rover power supply, which are always there in the background. And you can see as the compressor changes speed, you can see that the kind of relative magnitude of these different harmonics changes. In other words, they start to sound different. You can see there's a whole bunch of lines right around here, around 500-600 hertz. That's the resonant frequencies of MOXIE itself. That's MOXIE rattling. Tremendous amount of information in here we've only started to mine.
Question?
Yeah, go ahead.
Okay, sorry to interrupt. You're talking
Please.
about listening to the sound going on Mars.
Yeah.
Is there a speaker on the device there such that it could produce sounds perhaps a human saying hello, and then use the microphones to hear how that sounds.
Wouldn't that be cool? Another mission, and the closest thing we've got to that is actually MOXIE, which is, it's kind of, if people had the time, that's why they'd be looking at it. The MOXIE compressor is kind of one of the few things we can turn on and listen to. I mean, you can also, again, find online recordings of the rover moving, which sounds absolutely awful. If your car sounded like that, you'd take it into the shop. But you can hear that online, and you can hear the wind blowing. The spectrogram I just showed you was in the middle of the night where the wind is dead. But I have others where it's in the daytime and you can see all this low frequency bursts coming in from the wind noise. So we can hear the rover moving. Said you can always hear the pumps. You can hear the sound of the wind, and you can hear the MOXIE compressor, and that's kind of it. So we've only recently processed these data in a way that's satisfactory to allow you to hear it. One of the weird challenges is that almost any little app you get for playing sound, the default apps you get are filtering out noise, and everything in this recording it generally was interpreting as noise. So it was actually rather tricky for us to play the recordings even when we made them. But we got a sound wizard in to look at this, and I'll play two things for you quickly, and you should get the sound. So this is just MOXIE turning on, okay? And it's been heavily filtered now. So most of that background is missing. It'll turn on in a moment. Okay, assume you could hear that. Somebody give me a thumbs up. Okay, I see people nodding. Now this one is when MOXIE's already on, but the motor speed is changing, and I love this recording because it just really sounds like a motor ramping up and changing speed. Now here it is at one speed. And you can hear the volume went up, the pitch went up. And there it's slowing down. So you can imagine if the bearings start to seize up, you'll hear it on here, or you'll see it in the spectrograms.
Hey, Mike.
Anyway,
somebody posted a question of, have you tried listening to the helicopter?
Yes, there are recordings online of the helicopter.
Cool.
Yeah, so they're all there. I'm going to skip the rest. There's only a couple of slides. One is, we had a graduate student who studied the full-scale system. He called it BAM for the big, quote-unquote, atmospheric MOXIE. Okay, you can use the acronym however you want. The thing I took away from this out of a 350-page thesis was kind of this one figure that's showing me right now MOXIE runs very inefficiently, that most of the power either goes into the compressor or into heat loss, but we always knew that would improve radically when we scale it up and we start running at the compressor at lower pressures, which we intend to do. And he just verified that almost all the power would go into physics, would go into literally this dark blue is ripping apart the molecules. You can't get around that. And the bright yellow is the process of turning the gas into liquid oxygen, which also takes power. These two things are fundamental physics, and the stuff in blue and other colors is, just kind of the engineering cost of doing business, and really confirming the fact that this will be an extraordinarily efficient system when we build it full scale. So that's kind of the future. I do have this idea that as we start, as this base, this Martian base kind of develops over time, eventually we'll start retrieving water ice and we'll do co-electrolysis and co-processing of water and CO2 to make fuel and oxidizer and other things. Right now we can't make fuel because we don't have a hydrogen source. And what, the current generation, what we're doing now, the CO2 only MOXIE, will start to find a different role. And what I imagine it as a kind of the mini split for the future Mars base, where you have a device that goes on your wall with an external compressor that gives you heating and cooling and scrubbing of the CO2 out of the air and make up oxygen. Whether you're talking about a rover or a habitat or whatever, that's the device I would like to build next, is something that's, again, it's kind of the scale of your mini split that will be a general purpose habitat climate conditioning unit, including oxygen supplies. And with that, I have talked more than long enough. I appreciate you guys giving me some extra time. It takes a village. When it was COVID, we couldn't do a group photo, so we stuck together a lot of photos of the team members. But I'm going to leave you with that, and again, take questions for as long as you guys have patience.
I have a question with respect to the soil. Besides breeding, of course, humans have to eat.
Yep.
And, I can understand you bring seed with you, but why is there a feeling that you can grow something in a Martian soil when there are no organics there?
Well, that's, one question you have to address is whether it's safe, first of all. When we flew the MECA instrument that I was also the PI of back in 2007, the original motivation for that was also funded by human exploration. I've been around with these guys for a long time, was to ask whether it was safe to grow things in Martian soil. And what we found was, in general, yeah, it's good stuff. It's kind of neutral pH. It has some carbonates in it, which even on Earth, that's why we tend to have neutral pH in our water, because there's carbonates are a buffer. It had all the kind of usual cations and anions, magnesium, calcium, sodium, the usual stuff. But as you point out, it's not so much organics, but it's nitrogen poor. And you need fertilizer to grow things well. So you would have to add fertilizer, as you often do on Earth. Sterile soil is a good thing. When you buy soil at the garden store, it's usually sterilized, so you're not starting with microbes necessarily. You don't need them. You need is nutrients, is inorganic nutrients to grow stuff. So the biggest problem in my mind is getting rid of the perchlorate. That turns out to be easy in that it washes out quite easily. You want a recycling system so that you can wash your soil and then evaporate the water and recover it and just leave behind some perchlorate to make the soil safe to use. But other than that, it's not any different from when people do, well, in fact, you don't even need soil to grow food. You can do hydroponics as well. What you need is water.
Okay,
But the soil will work.
have they tried, for example, growing things in lunar soil, which
Yeah.
we have samples of?
Yeah, we don't have so much that you can do it, you can do it on any large scale. But I believe there have been some, well, I don't know of the answer to that. I think people have done that. I'm not certain. Because the lunar soil, even though there's many, many kilograms of it, is still kind of precious. And you have to apply for experiments. But, as I said, the soil is mostly holds up a plant more than it does anything else. You can grow plants in water and provide the same nutrients as you do in soil. So there's no reason to think it wouldn't work as long as there's nothing poisonous in there.
Okay, thank you.
Hey, Mike, how long will MOXIE run?
Well, that's a good
In other
question.
words,
There's two things that determine that. One is how long they keep funding us. And, the convention is within the science directorate, which is running the mission, that they pretty much keep funding you as long as the wheels keep turning. Within the human exploration directorate funding MOXIE, their tradition more is we fund an experiment until we're satisfied that it's done its job. So right now we have secured funding for another year, and we're hoping to get that extended. It's not obvious. So there's that part of it. Running every month or every 2 months, I don't see any reason we can't run as long as the rover runs. After, we can run up to maybe 100 times before we have to start cutting back our production. So as long as they keep paying us to do it, we'll keep running it.
What's the advantage of running it continuously? In other words, what do you continue to learn once you reach a certain point?
No, that's a very good question. So far, we keep coming up with individual things we want to learn. The next thing we're doing, as I mentioned, is looking at this feedback mode for maintaining constant pressure, and what that will allow us to do. And that's not just an arcane thing. Right now, we've been running in the middle of the night or the middle of the day. If you try to run at dawn or dusk, where the temperature's changing rapidly, it won't work so well. And we currently have to customize our run sequence for daytime and nighttime. So we need a smarter system. And we can do that in the laboratory. We can build more sophisticated software. But I'm almost afraid to tell you guys. This thing's running on an 8150. Did I get that right? And it, which is kind of like probably this goes back to the 80s. These little 8150 processors, and your toaster is smarter than MOXIE. I'm certain of it. Right? So we're very, very limited. The reason NASA does this is they're small, they're low power, they're high heritage. We know they work. You can cheaply buy them not only buy them in radiation hard packages, but in fact we don't even have a real 8150, or is it 8051? I always get confused. Must be 8051. But you can actually drop it in as a library block in an FPGA, which is what we do. So we're very limited software, and the first thing we want to do is use its full capability. So that's still to be done. And then the next thing we want to do is actually downloading software updates, which we have not yet done, to try to make the system smarter and smarter. So one reason is to learn more about controls in ways that will make us robust to running all times of day and not just select times of day, and not having to customize each run. The other part of it is just to continue to show robustness. At some point, the compressor is going to fail. This was one of the weak spots within our constraints for Mars, and it's for reasons that can be overcome by engineering. But the basic problem was that, if we just flew a commercial compressor, the bearings would shake themselves to pieces on launch. So they had to increase the load on the bearings, which shortens their lifetime. We need to find an engineering solution for that technical problem. It's doable, but ultimately, we'd like to learn how MOXIE ages. And so far, it really hasn't. Okay, so that's another advantage of continuing to run.
Mike, let's see, I'm just fooling around. So someone, George Slate asks, what about this project worries you the most?
Other than the money? Well, I'm worried that we're going to get greedy. And, the risk, every time you run, there's a risk of making carbon. And once you start down that road, it's sort of a slippery slope. You start making carbon, your area-specific resistance goes up, means you have to run higher voltages to get the same current. the more you run higher voltages, the more you make carbon. It can get pretty ugly pretty quickly. And again, kind of almost overconfidence. Well, we can run a little higher current. We can make a little more oxygen, and then you run it one day, and we say, "Oh crap! We just deposited a load of carbon on our electrodes, and the production went down." So I guess that worries me.
I have two questions, and maybe you answered the first one because I came a few minutes late. But MOXIE, just like the DACs on Earth, is breathing a lot, and in a dusty environment, what do you do about filtering?
Oh, that was something I was personally particularly interested in and pursuing, and it's one of those rare times when nature is kind. We thought this was going to be a huge problem because if you look at not so much for MOXIE on Mars now, because we only run an hour a month. But if we're going to run for 10,000 hours straight with a future system, and you look at the dust content of the air, you're saying you're going to have to filter out many, many kilograms of dust. Okay, many kilograms. And what are you going to do with all that? And how are you going to change your filters and, et cetera? It turns out we actually did experiments. We went to Denmark where they have a bright red, fire engine red Mars wind tunnel. They can accommodate dust, and we can put filters in it and compressors, and we did all that and simulated the system. And we found that we were looking for was the relationship between the dust loading and the pressure drops. And the reason that was a concern is that the Mars pressure is already so damn low that even a very small pressure drop can just choke the whole system. You get the kind of lint on your filter that you get in your clothes dryer, that could be game over on Mars. And you don't even notice it on Earth because the pressure's so low to start. What we learned, though, was that there were a number of experiments where, the air was drawn in, the air was flowing this way and was drawn in this way. In other words, the air had to turn, the airstream had to turn to go through the filter. And when we did that, we got no dust at all, basically. And we did a lot of models of that and discovered that, the air is so thin that while it can carry dust, the dust can't follow it around corners. So if you do something simple, like we've done on MOXIE, and you have a baffle, so the air is drawn in through a slat, and the point of the baffle was to prevent direct impact, of dust and pebbles. That's sufficient to actually kind of filter out most of the dust, even without a filter. We have a big filter on MOXIE, but scaling it up 200 times is not feasible, and that's why we.
But then at the turn, wouldn't it build up and after a while just provide blockage?
Well, you need to provide. I mean, this is an engineering design issue. You need to provide either some kind of a sump that collects it, or else just a system that will dump it and have it fall on the ground rather than accumulate in a sump. But it's a lot easier to collect a bin of dust than to have to,
Right.
to get it, to scrape it off a filter.
So it will be like a cyclone type of device that is used in many installations on Earth. Okay.
Yeah, that's exactly right. It's like a cyclone, but it's a lot simpler because the air is so thin.
Great.
Umesh, you have a question?
The second question that I had is related to the slide where you mentioned that your requirement was 6 grams. The goal was 8, and a couple of times you pushed it into the 10 plus region. And then you mentioned that you did that shortly because it was risky and so on. What happens if you actually burn one accidentally? Do you have a backup, or how do you make sure that you have a circuit breaker of some sort to protect the system from burning itself?
Yeah, the Achilles heel of the system is the software. And there were those of us who were very disappointed by the decision to use the 8051s for the electronics because they're so low capability, and we could have gone to a Leon processor, rad hard. The decision was made by the project to keep it with the 8051s. And that limited the extent to which we could really have a rugged fail-safe design. But there are a number of parameters that we can specify, a number of safety limits. And if those safety limits are reached, the run will abort. If we do that properly, and in principle, the damage can be limited, can be constrained by these fail-safes. But that means the next time you run, it doesn't heal itself in between. So the next time you run, you have to kind of start from what you consider to be the failure point the last time, and we can't do that too many times.
Thank you.
So Umesh,
Yes, hi. This may seem like an elemental question, or elementary question, also elemental. I was looking at the slide where you were talking about the voltage and the wires and the conductivity that I gather you would have preferred to use something like copper if it would have worked. What about something like gold? Now, certainly it's going to melt at those temperatures, but is there a way to use gold in some form because it doesn't degrade? Believing it doesn't degrade at that pressure and a temperature either, in some sort of a liquid form as a conductivity means?
Well, I mean, I think it's an easier problem than that. I think there are materials like platinum you could use that would be low conductivity. One of the things that happens on an experiment like this, a flight instrument like this, is that incredible conservatism and reliance on heritage kind of kicks in. So, for example, I mentioned those heater carriers that carry the heaters. We want those to be highly thermally conducting and obviously tolerate high temperatures. So something like silicon carbide would work. We tried silicon carbide and it cracked. And then, I thought we should have a silicon carbide insert to be a heat diffuser, but that seemed too complicated, so that they tried cadmium, a pure cadmium, no, chromium, sorry, to say cadmium, pure chromium, and which makes perfect sense, and you can buy chunks of chromium and it works. And, the project management looked at this and said, oh, chromium is not a material that really has the right certs for use as a bulk material. That's not what they sell it for. They sell it to melt down and coat things. And if we don't have the right material certs, we can't be sure one batch works like the one we tested. So they backed away from it. And they went with Inconel instead, and as a result, we have lousy thermal conductivity. Okay, so that's the same issue with the wires. There are solutions out there, and it was more a matter of, what has proper flight certification, for a mission of this scale. When we go to do it for the full-scale system, yeah, they'll put in the time and money to test out things like platinum wires and make sure that they work, rather than relying on existing heritage and certs. So the problem can be solved, in other words.
My second question.
Mike, I think we've gone 15 minutes longer than normal, which is great. Good evidence that there was a really interesting talk. And I wanted to thank you a lot for spending the time with us. And I'm sure we'll have continued interest now that we know a little bit about how MOXIE works.
Well, listen, I thank you for inviting me. As you can tell, I love talking about this stuff. And not only do I love talking about it, but if this is ever going to fly with people, it will be because it's so ingrained in everyone's sense of what a Mars mission looks like, or what that architecture looks like, that it's not, hey, remember that crazy thing we did back in the 20s with MOXIE? Maybe we should use that. It's, well, of course, you have an ISRU system and a power plant, and that's done by spreading the word. That's the only way to do it. So you guys are helping me out, helping out the project, helping out the future of MOXIE, and I thank you for the opportunity.
Just a quick point, if anybody's interested, since I volunteer at the Museum of Science on the Saturdays, the new exhibit on AI at the Museum of Science has two robotic devices that you can look at from slightly a distance. One is the famous Spot the Wonder robot dog from Boston Dynamics. And the other is a full-scale model, but not functional model of the rover we've been talking about.
Yeah, I
So-
think I'm signed up to do some kind of a talk associated with that, at least one or
So
two.
if anybody wants
as
to go
well.
over there, and you don't even have to pay money, you can come in and walk down the hallway from the parking garage, and there's a big glass window, and you can look right in. It's right there. You can be a meter away from it.
Michael, can I ask you a
Ted,
question?
did you have a different question as well? Because I can field that after we adjourn if you want.
Yeah, I had one other question about scaling, but going from this small laboratory curiosity to a full-scale power plant or ISU plant, you would think you'd want something in between as a test of real industrial kind of capabilities.
Not really, not really. I mean, we would have sent it full scale now if we had the means to. It just gets easier.
Okay, thanks again,
Okay.
Mike. Appreciate
Thanks
it.
again for the opportunity.
Yeah.
You bet.